We want to see how to determine the radius of convergence and the interval of convergence for a series. You may need to review some of the convergence tests from Calculus 2. One of the series that we studied in Calculus 2 was the geometric series, where we had some number raised to the n power. Well, what we determined was that if the number was smaller than 1, then the series converges. So what we're going to do is change our series so that it's x to the n, where x is a variable. And here we can say that it converges when x is less than 1. Well, the absolute value of x is less than 1, which means that x would be between -1 and +1. So we say that the interval of convergence is -1 to 1. Here is a graph of the interval of convergence. Now, in determining the convergence for this series, we're going to use our ratio test. In the ratio test, we have the limit of a sub n plus 1 divided by a sub n, the ratio of the next term in the series to the term before it in the series. And we know it converges if that comes out to be less than 1. So let's see how that applies here. If we substitute an n plus 1 everywhere there's an n, and then divide by the original series, that will come out multiplied by the reciprocal, and then we can simplify and try to find the limit of that. Well, a little bit of simplifying gives us this. We can split this apart. When we're doing the limit as n goes to infinity, the absolute value of x minus 3 has absolutely nothing to do with the n's, so we can take that out of the limit and then do the limit of n over n plus 1. Well, as n goes to infinity, that's like a polynomial, n to the first power, n to the first power, which comes out to be a 1. So this series converges if the absolute value of x minus 3 is less than 1, which is x between 2 and 4. Now, what we know so far then is that the interval of convergence is from 2 to 4. Well, from 2 to 4 means the radius of convergence is a 1. And notice that's what we have right here. This is centered at 3, and it has a radius of convergence of 1. Now, in applying the ratio test, we know that it converges if the ratio is less than 1. Here is the interval of convergence that we found from the ratio test. We also know that it diverges if x is less than 2 and x is greater than 4, but we don't know from any of the tests what happens when x is 2 and when x is 4. So we need to test the endpoints individually. So when x is a 2, here's what the series would look like. That would be the alternating series. That's harmonic. We studied that back in Calculus 2. That converges. If x is 4, it's the harmonic series, not the alternating harmonic series. The harmonic series diverges, and we at the interval of convergence to be 2 included and 4 not included. So let's test this one using the ratio test. Now again, the absolute value of x inside of the limit is exactly like having the absolute value of x outside the limit, since it has nothing to do with the n. And then we simply want to do the limit of n plus 1 as n goes to infinity. Well, since that's n to the first power plus 1, as n goes to infinity, that's going to get larger and larger and larger, so that's going to go to infinity also. Now, that simply tells us that there is no convergence. Well, there's no convergence for that series, but it converges at the center of that series. Remember, this is x to the n, so it's centered at x equals 0, so it has to have the same value at x equals 0 as whatever function it's modeling. In the previous lesson, we did some algebra and some derivatives to come up with this 6th degree polynomial to model e to the x. Well, what we could do is kind of expand this out some and come up with what we call the series representation for e to the x. We're going to test this series for convergence. So we'll use the ratio test, plugging in n plus 1 for each n, dividing by the original series, inverting and multiplying, and then simplifying. We come up with this. Now, again, the absolute value of x could be taken out of the limit, and so we want the limit of 1 over n plus 1 as n goes to infinity. Since the top is a constant and the n is going to infinity, then that's going to 0. Well, 0 is always less than 1, so the series converges regardless of what the values of x are. So we say that the radius of convergence is infinity. One more example on finding the interval and radius of convergence. This time we'll use the root test. Here's what the root test looks like. If we do the limit as n goes to infinity, we see that we get just x minus 2, absolute value of x minus 2 over 4. And the root test says that it converges if that is less than 1. So we set that less than 1 and solve for x. That gives us our interval of convergence except for the end points, which we must test separately. So when x is negative 2, we end up with this. Now, when you add up a whole bunch of 1s, it keeps getting larger and larger and larger, so that never converges. And when we use x equals 6, we come up with this, which is diverging also. Therefore, we know that it only converges for the values between negative 2 and 6. And that would be our interval of convergence. Now, the radius of convergence between 6 and negative 2, we have a distance of 8. So that would be 4 on each side of the center of convergence, which is 2.